Hi, everybody. This is the state-of-the-art quantum computer that exists today, designed by Google in superconducting technology. Is one of the modalities that in a race now to create a quantum computer. The structure of it, and this is relevant for all of the superconducting companies, if it's Google, IBM, Amazon, Rigetti, all of them built the same structure. There is the controller in room temperature. This is an up converters and down converters of RF signals that taking a baseband signal, convert them to a signal between 5 to 8 gigahertz, transmit them via coaxial cable to this cryogenic system that each of you can purchase with a $700,000 with the installation. And all of what you see is just cables, okay? All of that is just coaxial cables. They're going to here to the bottom, and there is the quantum computing chip, which is just a resonator sitting near each other, and all of those cables connected to those resonators, so those qubits. And each qubit connected with 3 cables, one for control on the qubits to change the state, and 2 for the readout. That is the entire structure of quantum computing in superconducting technology. So every one of you that is an RF engineer, communication, radar can fully understand that structure. The qubit is just a resonator. If it's resonating, it is 1 logical, and if it's not resonating, this is 0. And if we're sending an RF signal, we can tune that to superposition between 0 and 1 because we are cooling, the temperature is very cold, and we can control on a single photon. According to McKinsey, quantum computing is going to unlock a market of $2 trillion by 2035. But the point is, as you can hear from the speakers before, that to unlock the real potential of quantum computing, you need about 1 million qubits. And when I say to unlock is to start shaping humanity, start to run an application that really changes something in humanity and not just to present that it is working or the physics and so on. In Google, presented in 2019, the supremacy, they totally proved that quantum is real. They ran an algorithm that you are not able to solve on a classical computer, and then they present another and another proof that it is totally clear you have a machine that if you will take the entire world and feed in with the GPUs, you will not be able to solve those problems. But those problems are still not something that starting to change something. And there is a paper that you can read and see that exactly that once we have such a quantum computer, we can break them. And this is why all of the money go to start to achieve that advantage. And of course, during that process, there is a lot of money. If you're selling a cryogenic system or cables or amplifiers, there is a huge market right now in quantum. This is published by DARPA. And they took all of the interesting applications and mapped them and say with all modalities, how much qubits do I need and how much operation do I have? And then you can see all of those dots are in applications. This is a 100K quantum computer. This is 1 million qubit quantum computer, and this is 10 million qubit quantum computer. And all of the dots, for example, to the left of the 1 million qubit line are an application that you can solve with with 1 million. So when we go to that journey 3 years ago, we say we want to bring the minimum viable product that will be deep inside the interesting place of the revolution. We don't want to focus to a 10 million because then you are putting a huge and very complex task, but to the minimum viable product that proves that we are really deep in the advantage. This is how Google going to build that advantage. The cryogenic system, and you can understand from the cables, is limited to about 5,000 qubits at the maximum. So they're going to connect hundreds of cryogenic systems to each other. This was the plan so far, if you look on the last 4 years. This is going to have the size of a soccer field, cost $1 billion, and consume 12 megawatt of power consumption. what we was able to do in QuamCore 3 years ago, we found a way to take to solve the scaling problem, and you can guess that this is the cables, and to shrink that soccer field to a size of a box, 55 by 52 by 28 centimeter, and to reduce the cost from $1 billion to $1 million, and to reduce the power consumption from 12 megawatt to 20 kilowatt. We spent 2.5 years without touching anything, just to work on the architecture and on the design, and to wrote patents. And practically we achieved with that a line of sight to reduce 1,000x on size, cost, and power. And with that, we started to build that computer. And the most important part on that is not just to reduce 1,000x on all of them, but when we go to such an approach, it becomes much easier to build that quantum computer. And this can reduce also the time to market with that advantage. Before I will tell you exactly how we are doing that, a little word about the team. I spent 10 years in the Israel Intelligence Unit, 8200, developed multiple signal intelligence system, a lot of hardware algorithms, board design, FPGA design, starting from invention to full deployments of multiple systems, 13 years in the semiconductor industry in Broadcom, Intel, and Mobileye. I developed chip for backhaul communication and 5G for Apple. On my last role, I co-founded the IC Radar organization, direct investment from Amnon Shashua, invented the 4D imaging radar in 80 gigahertz, wrote about 40 patents on that, and that's fully deployed to Volkswagen car in mass production line, and I had the honor to get the Intel Oscar Prize for that co-foundation. My partners, much smarter than me, Professor Shai Cohen-George and Professor Serge Rosenblum from the Weizmann Institute and the Technion. They did their PhD in Yale and Berkeley and came to Israel and co-founded a superconducting lab at the Technion and Weizmann Institute. They both produce, measure, and publish qubits, working qubits in superconducting with state-of-the-art performance. Serge is holding the world's record of qubit with the highest coherence time. And Professor E.B. Friedman from Rochester University is an expert in digital logic in superconducting. And I will say it again, digital logic in superconducting. It's called SFQ. This is something you need to write now and look for that. And this is the point of how we are doing our breakthroughs. And so what we did practically, the problem with the quantum computers are fully working. Yes, Google presented full stack with the 100 qubits, everything is fully working, and with performance that you can scale to millions of qubits, no doubt. The problem is how you control on those qubits. You cannot scale with controlling with 3 cables on each qubit. If you want to build the 1 million qubits, you need 3 million RF cables. This is crazy. And what you want to do practically, what we did, we took the controller and integrated that inside the cryogenic system. The cryo system is cooled down to 100 millikelvin, to 10 millikelvin, and limited to about 100 microwatt power consumption. And controller for 1 million qubit is about 40,000 watt for 1 million qubit on the state of the art. We was able to find a way to reduce 1 billion x in the power consumption of that controller, so we can integrate that inside the cryogenic system and reduce all of the cables. So practically our quantum computer looks like that. This is a box sitting inside the cryogenic system. It's integrated the qubits in superconducting, but also the digital logic in superconducting, integrated with a flip chip technology on the qubits and control with bump bonds directly on the qubits and have a small digital communication to the outside world. This technology invented about some decades ago, and people created the CPUs with that. Why it is interesting? Digital logic in superconducting reaching 600 gigahertz and consume 10,000x lower power consumption. The point that this technology was not scaled because it was not able to find the market fit because this required a cryogenic system with 20 kilowatt power consumption. So it was not able to scale as the CMOS did, and it's lost for the CMOS. But for quantum computing, we recognized 3 years ago that this can be the disruption for quantum, and we used that to build that. So we integrated that controller inside. We took that technology from 4 Kelvin, did a modification to 10 millikelvin, and designed a unique architecture, full stack, to do that control. Raised $35 million from leading venture capitals. We closed partnership with SkyWater that produced that technology in the past, and we working very hard with them to do a modification of that, to do the shift to the 10 millikelvin. They are just acquired by $1.8 million yesterday by IonQ, and business are continue. And we have 2 targets. I'm finishing. Building 1 million qubits by 2033, 1 million qubit quantum computer, and present in 2027 full prototype that we can present digital control, controlling on qubits inside the cryogenic system. I just say no time, but all of the ecosystem understand now what we are doing, and they are all shift. IBM with SICK got DARPA program win. Google acquired Atlantic and transferred to that digital logic. And D-Wave just published that they technology, because they are working also with SkyWater, can scale quantum computing with integrated controller. That's all. Thank you.